So yes, so Albert, if you'd like to introduce Sandy, you may.
Sure. Okay, let's start now. Okay, welcome everyone. Welcome to this condensed matter seminar. It is my pleasure to introduce to you Dr. Sandy Adhitia Ekahana from the Paul Scherrer Institute in Switzerland. And for those of you who do not know where Paul Scherrer Institute is, what it is the largest research institute for natural and engineering sciences within Switzerland. And from the slide, you can see how beautiful it is. So let me introduce Sandy. He's a PSI fellow in Spectroscopy and Novel Materials Group under the supervision of Professor Ming Shi. He received his D.Phil or PhD from Oxford University. And he's also our alumnus. He belongs to the third batch of the Division of Physics and Applied Physics in NTU, where he got a first class honors. During his time in NTU, he worked with Prof. Sam Zhijian, working on semiconductors with ultrafast laser technique. And when he went to Oxford, he worked on topological materials using ARPES, which is angle resolved photoemission technique. And currently he's doing his postdoc in PSI, working on magnetic Weyl Semimetals in the SIS beamline. So we are very happy to have one of our alumni come and give a talk to us. And for you undergrads in the audience, you can see what our alumni have been up to. And I will give the time over to Sandy.
Yeah, thank you, Albert, for the nice introduction. So good afternoon, everyone over there in Singapore. It's morning here. And yeah, so I'm invited here first as an alumni to share some of my work. As an introduction, I will also share some journey, some story that I have before in NTU and about my career path so far in physics. So yeah, as been said, so currently I'm a PSI fellow in Paul Scherrer Institute. The funding is given by the sponsor labeled in the bottom of the slide. So it's the National Foundation and also Marie Curie and Marvel also. So Marvel in here has nothing to do with the Marvel, the movie. This is the collection of a theoretical group that is predicting a new stuff. And then after that, there is also another experiment group join this Marvel group to have a collaboration together. So this is where the context where I'm working. So yes, I'm working on magnetic Weyl Semimetals. This is like the continuations of what I've been doing since PhD. And yeah, so to give you a bit background story about myself. So I'm the class of 2011. So I graduated in 2011. So this is me. And yeah, working with Prof. Sam Zhijian and also Prof. Alfred Huan before. So it was a great experience for me, basically, during my time in NTU. That, well, third batch means everything is new. In fact, I think I'm the last batch who basically experienced the first year of my course is running around NTU from South Spine, North Spine, looking for class because practically SPMS building is still under construction. So yeah, and then only in my second year, then we start to enter that building. So yeah, it's been great experience for me. And then because it's really new, so that's why, I mean, I can see that at that time there are a lot of opportunity, and then I grabbed some of the opportunity to work in the ultrafast laser group under Prof. Sam Zhijian, building a lot of techniques that in the end, I learned a lot during my undergrads to really build stuff, like contacting the vendor, do all this preparation to really build something useful, like setting up a time resolved transient absorption, white light transient absorption, TR MOOC also. So yeah, there have been a lot of like experience going on, and then using the experience, actually, I think that's also one of the reason why I can be accepted in Oxford, because then in Oxford I also aim to a new group. And unfortunately, I don't really have a lot of me photo. I mean, I don't really have a lot of photos of me in Oxford, and this is just me during the graduation. So I work with Yulin Chen in Oxford. Well, initially the plan is I need to build a laser ARPES over there, but then yeah, you see that the difference between new university and an old university is sometimes in the old university you just have a lot of bureaucracy here and there, and then in the end I end up having no lab at all. So that's why becoming an experimentalist without any lab-based home base is really tough, because then I really move around, walk around any ARPA station around the Europe basically. So I start in Diamond Light Source. So Diamond Light Source is the synchrotron nearby Oxford, where I practically learned my first experience with ARPAs, and then just learn all things about ARPAs over there. So this is like my home laboratory basically. So then other than this, I also play around in Soleil. This is in France, another synchrotron. So you see, all my PhD life basically just working around inside a donut, where you have a bigger donut in Diamond Light Source, and then you have a kind of like smaller and smaller in other part of Europe because they are older. And other than in Soleil, I also work in Bessie, and unfortunately I don't have the picture. I only have my my name tag at the time. And lastly is in Electra, where again I do not have any picture of that, but I have my last chocolate that I get over there. So anyway, my point is, yeah, throughout my PhD life, I basically I'm just running around synchrotron, making any experiment over there, doing ARPAs. So that's me. Then after that, now I end up here in Paul Scherrer Institute, again working inside this donut, doing with the same technique, which is ARPAs, studying another kinds of topological material, which is in this case is magnetic Weyl semimetal. So that's about me, myself. And by the way, if any of you have any questions, just feel free to raise your hand, and then I can address the question. So the title of my talk here is basically, here. So Dirac or, sorry, it's not off, sorry. Dirac or Weyl semimetal in iron tin. So an investigation from ARPAS. So is it Dirac or is it Weyl semimetal that actually, is it Dirac point or is it a Weyl point that exists in the iron tin? So to cut the story short, actually the answer is Weyl. So that's it. I mean, that's basically the gist of my talk. But then now the details of it is, why is it that we have kind of this discussion whether it is Dirac or Weyl in here? So before I go into the detail, here is my outline. So I will discuss the background itself about the iron tin. So why we have this kind of discussion in the first place, and then after that, I will introduce what we have done so far using ARPA system, and practically, and in particular, I will present the result of our recent laser ARPAS measurement on this system, apart from the synchrotron ARPAS measurement. And in the last bit, I hope I still have some time, that I will also discuss a bit about the representation learning that I did and I applied to this overall team of ARPAS analysis that actually helped me a lot in the analysis of the laser ARPAS. So that's about the outline. And before that, I will introduce a bit about, so what is ARPAS? So ARPAS is angle resolved photoemission spectroscopy. So basically, it's a photoelectric effect. You shoot a photon. If the photon has enough energy to overcome your work function, so then your electron can be ejected out with the kinetic energy of the photon energy minus the work function. And then, so from here, basically, if you have an X-ray or you have something bigger than that, you can eject a lot of bunch of electron, and then this electron is basically hemispherically going out from your sample. So in this case, I'm talking about a very smooth sample where you have a well-defined surface like in this picture. And then the idea is that also each of these electron going hemispherically out carries information. So what kind of information is that? Obviously, you have the information of the energy. So, and then also the information of where it's going out. So in this case, it's represented by this angle. I call this phi, and also you have another dimension, which is theta. So typically in a ARPES analyzer, you aim that ARPES on one a particular angle, or rather you aim your sample. It depends on the setup. So in any way, if you're on one certain configuration, this analyzer can get the information of the energy and also a certain angle opening that is allowed by this analyzer. So from there, you will get the information, and then you will get the picture of how the band structure looks like. So then in short, if you're using ARPES, you are looking directly at the band structure of the sample, although it's not really exactly band structure. But anyway, you get the idea. You get the picture of the band structure directly, and then if you collect at one angle, and then you collect at the other angle, and then you complete for the whole angle. In principle, if you collect all this bunch of cuts together, then you will get the information of the two-dimensional area with the energy in the z-axis. And then if you combine them together, for example, you cut this energy along the Fermi level, then you will see how the Fermi level looks like on that particular sample. Okay, so and then again, the information that you get in here is still an energy as a function of angle and angle. And then there's another formula that you can use because you have information of where this electron is going. So then you can know what exactly is the momentum of this. So you can convert that energy as a function of angle, and then you can use this formula. You can convert that energy, and energy become a momentum in principle. So in that case, then you get the real band structure, right? I mean, you have E as a function of momentum. That's your band structure. So then with ARPES, you can get the idea of how the band structure, but then this band structure, this momentum is only along the two-dimensional momentum that you're looking in this particular sample. So you have the energy, you have the momentum along this direction. Then what else the ARPES can do? So ARPES can actually also read the momentum perpendicularly. And how do we do that? We do that by aiming the analyzer and the sample basically perpendicular to each other. So if we do that, we change the photo energy. So this is where the you can only do this in synchrotron because we have a tunable X-ray photo energy. So by tuning the photo energy, you collect all the cuts together. You are probing different momentum in Z direction along your sample. I mean, along the Z direction of your sample. So with that in mind, so that means now you can use that information to convert it into the KZ by using this formula. So now you have a complete information of your band structure in principle. So you have your energy, you have your Kx, you have your Ky, and then you have your Kz. So now you're complete. So in principle, yes. So with ARPES, you can study the band structure, any band structure, of course, as long as it is well defined, and then you can study the complete band structure, and then you can see how the Fermi surface looks like, for example, in here, and you can study a lot of things going on in here. And this is where actually this is a very useful tool that has been used so far in the world of topological material when you start to study about the band structure of the material. So this is the introduction of what ARPES in principle, in general, is all about. And the next development in ARPES is that, well, if you're using synchrotron, your beam spot typically is 100 down to 50 micro. So then if you're using that big kind of beam spot, maybe if you're studying something that has domain, for example, like what I'm doing, which is magnetic material, where magnetic material, you should expect you have a domain. So this domain might actually kind of like convolute or disturb how the band structure looks like when you are reading it with the analyzer. So this is the next development in the ARPES, where you have a micro, or you also have a nano focus ARPES. And in this particular situation, or in this particular scenario, I'm using micro focus laser where I'm using laser and then I focus it down, I narrow it down to 1 micrometer. Well, I mean, if it is the FWHM is about 1.5. So that anyway, it's down to that size. It's really small. We like smaller in 1 order than the 1 and 2 order with as compared to the synchrotron. So in this case, hopefully by using this micro focus laser, I can study individually where individually the domain as compared to the synchrotron, where basically you get everything together. And yes, using laser, you still can also use the same formula that you have before. Then apart from this, you can also do a scanning, because now you are in micro. So instead of just focusing on one place in your sample, you can scan your sample. Oops. So you can scan your sample basically. So this analyzer basically you can scan the X and Y, and then on each X and Y position you will get a band structure, the E versus theta. So then after that, if you combine all of them together, then you will get a very massive 4-dimensional plus intensity data, which typically will be like 1 gigabytes or 2 gigabytes per measurement. So this is like the context where the tools that I've been using so far. And so this is the tools. And then now what about the system itself? So like I said, I've been studying this topological material. So what is it about? And as a very brief introduction, so this all started with this band structure that you have a simple band structure, conduction, valence. So what happened actually that at some point, if you tweak the crystal or you tweak something about the configuration or the spin orbit, and you can practically like bring this together down, and then it can at some point cross. Okay, and then when it cross, it create something what we call as the nodal line. And then if you have studied the introduction to solid state, you know that if a band structure cross, naturally it want to open up a gap. So this is actually the natural thing that happens. But then if you have something that is called as the band inversion in here, so where actually the top band and the bottom band is band inverted around this area, and then you introduce the spin orbit coupling, for example, and then you introduce the gap. So at this particular area, you have an inverted band. And this inverted band is what we call is non-trivial. The reason is because if you compare the bulk of this sample, you compare it with the vacuum is trivial. So there should be something going on so that you will make it like trivial again. I mean, band structure cannot by itself like be flipped like it is. So yes, that's actually what is happening on the surface. So like the interface between your sample and the vacuum, that is actually trivial. You have something that we call as the surface state. So this surface state is like the consequence of this, because you have a band inversion. So you need to have it reinverted again at the outside. So, and also this is what we call as topological surface state, because the reason is because, well, in principle, you cannot really destroy this unless you really destroy the thing that is making this topological. So in this case, if it this is what we call topological insulator or any other Z2 invariant system. You can destroy this by breaking the inversion symmetry or introduce some magnet. But then in principle, other than those two things, you cannot destroy this. Like if you introduce some kind of like impurities on the surface, you will not really destroy everything. So with that, there is a like another progression on this idea that what happens if you actually introduce a certain protection in the symmetry itself. So instead of having everything open up, at some point you have a protection. You have a protected crossing because of the symmetry that you induce. So this is actually what is happening in what we call as the topological Dirac semimetal. You have a protected Dirac crossing due to symmetry. For example, you have this in cadmium arsenic. You have a C4 symmetry that is protecting this. So yeah, then other than this, well, if you remember how your Dirac formula looks like, if you everything here is what we call as a massless Dirac fermion. So if you go back to your Dirac equation, if you put mass equal to 0, this is what you get. So you have a 4-dimensional thing in here, and then each of this sorry, yeah, you have a 4-dimensional here, which is actually represented by here. If you calculate this one, there are this is there are 4 degeneracies in here. And then if you notice, well, in principle, you can break this equation into 2. This is what we call as the Weyl equation. So this actually what has been like in about like 5-6 years ago. This is what is the hot topics in the condensed matter, looking for Weyl fermions. And then the way we can do it is actually by breaking this Dirac fermion. Can we do that? If we break the Dirac fermion into 2, then we'll get a Weyl points basically. So this actually has been done, and the first path that has been done so far is actually using what we call as the breaking the inversion symmetry. So if you break the inversion symmetry in your system, you can have a minimum of 2 pairs of Weyl points. So this is what has been found so far. And then the next thing, which is a topic of my postdoc, is actually then can you also find another kinds of Weyl semi-metal that you can get it by introducing the by breaking the time reversal, which is introducing a magnet. So that's why it is called a magnetic Weyl semi-metal. And if you have a magnetic Weyl semi-metal, the hope is that your Weyl points is odd numbers in pairs. So the minimum that you can get is a single pair. This is the ideal Weyl semi-metal. It's very hard, and then I mean, so far you cannot really see it. So so is there any experimental evidence for this magnetic Weyl semi-metal? Well, it turns out yes, there is. And then one of the first report is that in this Kagome cobalt tin sulfide, so CSS, I just call it CSS. So in this system, this Kagome system is a ferromagnetic in low temperature. So the structure is given by this picture. So everything, the magnetic moment is pointing up. So everything's so simple. And then turns out when you do the calculation, you will get an odd number of Weyl points existing right at this plane. And then if you project it on your surface, you will get 3 numbers of pairs. So 3 pairs of Weyl pairs in here. And then these Weyl points are connected by what we call as the Fermi arc on the surface, which is the like what you have in the topological insulator is the consequence of having a non-trivial topology on the bulk. So the picture should looks like the one in here. This is the calculation. So you have 3 pairs residing on this edge of the Brillouin zone. So you have 3 pairs connected by the Fermi arc, or in this case, the Fermi arc is here. And then in ARPES, can you really see it? First of all, it's really tough to get the data. And then this is one of my colleagues back in Oxford. He managed to get some data and then do some analysis. And then basically we conclude that this guy is basically the Fermi arc. And yeah, and yeah, and the reason why we can conclude that this is actually a surface state is because when you change the photon energy, like I said before, when you change the photon energy, you're probing at different kz position, right? So if it is a surface state, so naturally that means you're expecting that it should not change, because surface state should not have any dependence on kz. So this guy, when you change the photon energy, this guy doesn't change. So it's a very strong evidence that this is really a surface state. And according to the calculation, it is predicted that there is a Fermi arc on here. So we conclude that actually that is the surface Fermi arc. So then is it done? So because then it seems like everything is done, right? I mean, you have the Weyl points, and then you have the magnetic Weyl points. So what am I doing in here? Well, actually, there are other system that is that is also that we study also. So this is where my talk is. This is about the iron tin. So well, before I introduce the iron tin, so why is it Kagome? So what is it so important about this Kagome system? So first of all, if you do a simple tight binding model on this Kagome, no, this is similar like the honeycomb lattice in the graphene, right? So you are expecting something interesting going on the K points, which is true. If you just do simple tight binding model on this Kagome, you will get a Dirac point around the K point. And interestingly, for this Kagome, it is widely known that if you do the tight binding model, you also get a flat band. And flat band is very interesting because why on earth you have a flat band on a system that should be dispersing? So yeah, I mean for the undergrads, flat bands means something is really just stationary. So why you have something like that? So that's why it's very interesting. And then people has been trying to really pin down or really at least read in ARPES display what kind of flat bands that we can get in the Kagome. And then also, if you calculate the tight binding model for example, this is a simple single layer Kagome. If you calculate the bilayer Kagome, like in this picture, if you calculate the bilayer Kagome, the same thing happens. Like if you calculate the bilayer graphene, you have split. So and then you introduce more Dirac points, and then in this case, you are not only introducing two Dirac points, you introducing a Dirac ring in here. So that's actually like the reason, the background reason why actually Kagome itself, from the band structure point of view, is very interesting to really see if this prediction is true or not. And now about the iron tin. So iron tin is another Kagome system like the CSS that we discussed before. And it has interesting part also in the fact that each of the Kagome layer there is what we call as the breathing Kagome. So breathing Kagome means your size here is not really exactly the same. So like you see, yeah, like I showed in here, the size here is 2.5, and this is 2.7, so represented by a different color. So the Kagome itself is what we call as a breathing Kagome, so it's not really ideal Kagome. And it is interesting because the way that it is stacked for this iron tin, so you have a stack of Kagome on top of each other, which is like the bilayer before. And then apart from that, you have another stack of Kagome, and then they are like different by a certain translation. So you put it down, translate, put it down, translate. But in any way, it seems to me that you have an ideal system to study about this Dirac, right? Because previously in the tight binding, it is predicted now you have a Dirac ring. So, well, the thing is, it may not be that quite straightforward in this iron tin. First of all, because of this breathing Kagome system, so from the sample grower point of view, it is very natural. It is very normal if you see some kind of like twin domain in the first place. Twin domain meaning that, well, everything is the same. It's just that at different domain, one is rotated to each other by 60 degree according to the symmetry. And then this is allowed, and this is energetically also favorable. So you might have this kind of like random thing. So apart from that, iron tin itself is ferromagnetic, and it is more complicated than the CSS. So for the CSS, so far what we know is if it is at the very low temperature, everything is pointing along the Z direction, along the C direction. While for the iron tin at low temperature, most of the magnetic moment is pointing on the AB plane, which is along this Kagome plane, but not really exactly at the AB plane. It's a little bit canted by 20 degrees or 70 degrees from the top. Or this one, that means the theta here is 17 degrees if it is at low temperature. And at some point, it undergoes reorientation. So the magnetic moment can switch from down from the AB plane, a little bit canted by 20 degrees, and then you increase the temperature. At some point, it will go up. So that's the reason why I'm more interested in this system, because at first I hope that actually I can see some signature in the of the wall points, and then I hope that I can also study how actually the wall points behaves when you are in different magnetic environment. Well, that's the initial hope, and then actually the story goes to a different direction because suddenly well, actually around 2018 there's a publication claiming that, hey, we see Dirac point in iron tin instead of wall points. Okay, which is something that is already, yeah, it was much debated and discussed whether it is really Dirac points, or is it just some artifact from the ARPES itself that you can't really see. Yeah, the thing is, then this I lay out the background of this iron tin. So basically, the groups claiming that they see Dirac points. So what kind of Dirac points that they're looking? So they claim that on this picture picture C here, they claim that they see the Dirac ring, kind of like. So you see here, they claim that they see a Dirac ring, and then they also show that, well, there is no gap in here, so it must be the Dirac ring that is predicted by the tight binding, right? Okay, so but actually, that's not what we found. So well, first of all, if you do a DFT calculation on this iron tin, well, of course, naturally you will see a lot of Weyl points popping up, because iron tin is first of all, you have a lot of atoms in iron tin, so you're expecting a lot of bands. And then when you have a lot of bands close to the Fermi level, then you expect this band might cross each other, and then some of the crossing might be Weyl points. So that's actually like the basic guess that we had before. And then this is what we found. So we did calculation, DFT calculation, and then we even play around with the magnetic direction, play around when the magnetic moment is pointing along Y, along X, along Z, how the Weyl points is behaving, how they looks like. So we found a lot of Weyl points basically. So this is actually what we kind of expect. So actually in the ARPES, whatever that they are looking in here, one of them might be coming from the surface states of or the Fermi arc, or anything that is related to the Weyl rather than the Dirac. The reason is because you have the predictions of this Dirac point is really coming from tight binding, and then the tight binding itself only assuming a bilayer, and then this is a bulk, right? So if you have a bulk, and then you also have you also need to introduce interaction with the other layer. So obviously, if you introduce the interaction with the other layer, the Dirac points will just disappear as it is. So
hey Sandy, I had
yes.
a quick question. So how do I identify that it's a circle and not a point? So I guess your main point is that you're able to identify it as a Weyl point. And then these people point out that, that in this figure panel D, they say it's a circle. So how and why did they call it a circle? I can't see any. Perhaps you can describe a little bit why they ascribed the word Dirac circle to that that thing there, apart from the obvious thing which you said, which was, there was some concurrence from tight binding explanation, but maybe you could just explain a little bit, how they look visually from that ARPES data that you kind of showed.
Yeah, okay. So basically, I should say forward that our group never really see any Weyl points, because the predictions and the ARPES result is so complicated. It's so different. Well, it's not really that different, but in the sense that there are a lot of bands going on, and then the Weyl point position is really dependent a lot of, for example, the U value and everything. So we don't claim we see any we don't claim that we see any Weyl points, but we want to claim that actually whatever that they're looking, that they claim as a Dirac point, is actually not really exactly Dirac point. And what I understand is that the way that they do, like for example in here, they just follow how the band structure evolves. And looking at the way the data is so nice, they might do some symmetrization here and there. And after that, you just plot it. In this case, they plot the EDC. So when you plot the EDC, you can follow how the peaks actually evolving. So they like in here, they trace the peaks, and then they when you are in the position where you think the Dirac point is, and then you see there's no gap, at least from the ARPES. So ARPES can only say that, okay, we don't see gap. But in principle, whether you can really claim that gapless thing that you see is really a point or not, it's really dependent on whatever the prediction is. So I mean, like ARPES in itself can only see whether you have a gap or you don't have gap. When you say you don't have gap, you can always attribute it, we just don't see a gap. We do not know whether it is really gapless or not. So that's actually how I understand they come about to concluding, okay, this is a Dirac point. they found something that is gapless, and then they have a support in the tight binding, so they just combine them together, and they claim that this is a Dirac point, which is not what we see actually. So, and this is actually what we see. So this is how our ARPES data looks like along the K point, exactly the same thing that they are doing. So yeah, I mean, this is not only coming from, I mean, the frustration doesn't only come from our group. So actually there's also another group like trying to say the same thing, that we don't see that. I mean, what we see is that when we cut along the K points, exactly the same, roughly around the same position in here, and then we follow at different photon energy, which is probing at different KZ, well, if it is really the Dirac point that they claim, which is more or less a quasi surface state, right? Because you only predict this Dirac point because you have a tight binding model of this bilayer. So in principle, if this is really true, you should see that Dirac points happening at all different photon energy. So it should not depend on photon energy, because this is kind of like quasi surface state, right? So, but then that's not what we see. What we see is actually, well, you obviously can follow in here. This is the example of the cut one. This is the example of the cut two. So cut one is here, cut two is here. This is the KZ. That means this is a cut at different photon energy. So this is the cut at different photon energy exactly at the Fermi level. So even at the Fermi level, you can already see something is dispersing in here. At some point the band is there, at some point the band is not there. And then yes, the band looks very straight. You might also say that, well, there may be some kind of surface state contribution in there, but then there's also bulk contribution. But then by the end of the day, you can't really say that you really see a Dirac point. And another kind of like support that we have is also, well, just from a simple fact that when you're doing the DFT calculation, you don't really see the Dirac point in here. You see, if you cut along the K and you play around with the U value when you do the DFT calculation, no matter what kind of U value that you put, you will not see a crossing that is predicted by the tight binding. I mean, everything is so like reasonable, right? I mean, yeah, tight binding, you only calculate this bilayer. You don't really calculate the hopping to the other layer. I mean, I'm sure if you introduce the hopping to the other layer, yes, it will be more consuming in terms of computational time, but then you will open the gap. So then what's the point of claiming that there is a Dirac point in the first place? So you should not say that you see any Dirac point, because the DFT itself doesn't really show. Like our collaborators even like spend some time to just really play around with the U value. Maybe there is some U value that we suddenly see the resemblance of this Dirac point. Like the closest thing that he can get is around this value. Even so, this Dirac are still gap. So this thing doesn't really close at any U value. It will only go away if you introduce more U value. So this is where the like the situation, like the heat of the situation during like I think around 1 year ago when I joined. So then my idea is that, well, of course, okay, so if you really have a lot of this discussion, debates, and oh yeah, before that, actually, yeah, this is what I say. I mean, another group even claimed the same thing. This is in arXiv. I think they already published it now in PRB. So they also report the same thing, which is actually, you see, on the K points, we did not see the Dirac point. What we see is actually a combination of surface and bulk, which is also what we see. So then it's kind of makes sense now that you should not see any Dirac points on the K, because yeah, you have a bulk, so you don't really have an ideal Kagome. And then from what they report is also the same thing that we already report, that actually they see that when you are at different photon energy, this guy disappear, and then at the other photon energy you don't see anything. So it's very obvious then the top one is a bulk or bulk / surface state, and then the bottom one is a real bulk. So you have a combinations of bulk and surface, and if it is a combination of bulk and surface, so you can't really call them a Dirac point, because then it doesn't exist in your system. You only see a projection, so you cannot really claim anything. So then how do we answer then? Why do we have something interesting on the transport of this iron tin? Like you have in the magneto transport measurement, you have something interesting. So all this, we just say then now it should not be coming from any Dirac points. So it should come from the Weyl points that actually we claimed before. So then that's actually kind of like the final situation, or like our final say to this problem. So is it Dirac or is it Weyl? We just conclude that it should not be Dirac, it should be Weyl. And then how do we show that this is Weyl? Unfortunately, using a synchrotron ARPES, it's tough because you just have a lot of bands, and then even the calculation itself is not really that it's not really that straightforward. You have a lot of like things that you can tweak. So then this is where the next step that we did. Then we just go to the laser ARPES. We just do the ARPES using a micro focus thing. So then we can study each of the individual domain like individually. So we don't have anything convoluted from the other domain. And then so this is the situation. So synchrotron versus laser. So what is going on in here that you can see the laser beam spot is roughly this size, and then the beam spot of the synchrotron is around this size. So it's like way smaller. So with this, you can really study each individual domain. And then but then again, this is laser. So unfortunately, meaning if it is laser, you have a very small photon energy. So if you have a very small photon energy, you are really zooming in the Brillouin zone. You can't really go away from the gamma point unless you really like tilt it a lot. But then tilting a lot, it will not help you go to the K point. So I should I should satisfy myself with the gamma and then just study whatever that I can study over there. So what we found is that well, before that, actually, I study first actually how is the termination looks like in this system, right? I mean, now because you are really trying to study like spatial resolve band structure, so you really need to get rid of any influence of whether this is actually coming from the termination or something else. So this is what we did before we go to the laser, that we study the micro X-ray absorption to really see how the absorption looks like. From this measurement, basically the result is we conclude that the main termination that we see is actually coming from the tin termination. Well, if we go back to the to how this iron tin looks like, you can either have a termination that is terminated on the Kagome if you cleave it. Okay, so if you cleave it along the 001 direction, you either stop at this Kagome, this first Kagome, or you stop at the second Kagome, or you stop at this thin ring, or then you stop at this first Kagome, second Kagome, or the thin. So then basically you have three kinds of possible terminations in here, right? And then what we see is that from this X-ray absorption, the micro X-ray absorption, is that, well, if you compare this, looking at the tin peak, you see that actually mostly this is coming from tin, while the darker part we attributed to the Kagome. And then if you see the iron peak, you don't really see a difference because this is something to do with the way the layering is going on. So then you can just focus on what is going on the tin peak. So we conclude that, well, you have more tin coming out rather than less tin. So then we conclude that this is coming from the tin termination, while the minority termination is coming from the Kagome itself. So then at least from here we can get some kind of idea what kind of termination that we are getting when we do in the laser ARPES. And we also did the dichroism, the X-ray micro Scherrer dichroism, to see actually how the magnetic domain looks like. And then we conclude that actually the magnetic domain has nothing to do with the termination. Okay, which is good, right? So then now that means when I start to study this system with the laser, I will only worry on the fact that, well, mostly the surface that I'm looking is thin. If I see something minority, it may be coming from the Kagome. And then if there is any influence on the magnet, there should be a separate domain size or domain shape compared to the termination. That's actually my my ammo when I go to these laser ARPES to study it. So what do we found actually? So from this laser measurement, well, we found first of all something interesting that initially in one of the area, well, you don't really see a difference. Like you always see on the cut, you always see something electron pockets like this with a wing. Okay, and then the wings can be more lightened on the right one or more lightened on the left one, but then in principle it's the shape is like that. You don't really see any drastic change, so it kind of like make me sad at the time because then well, I'm hoping I see more things because, well, I mean, you have three kinds of termination, and then you might have something magnetic domain issue. Well, then turns out you only have one, and then okay, then we in the end just pick two different position where we see a different part of the wing is being lightened, and then we make a Fermi map. And then surprisingly, when we make the Fermi map, we see something interesting, which is first of all, the pattern of that Fermi surface is threefold, which is interesting in the first place because iron tin is supposed to be hexagonal. So then, since we are using laser, meaning more or less we are on exactly at the kz equal to 0 plane. So why on earth do we see any threefold instead of sixfold? Well, my conclusion at the moment is that this 6.2 EV that I'm using to probe, so it might not really exactly at the kz equal to 0. I may be away from the kz, a little bit away. So that's why now you have a threefold. And unfortunately, because of this information, when we go to the other domain, we see it flip. So this is interesting because then, okay, it's obviously the twin domain that we have been talking about. Then we kind of like prove the whole point that all this like complicated data that we see in the synchrotron, it might really be due to this complication due to the domain. And then in this case, it's the domain from the crystal itself that actually it can be twin. And to prove further that this is really a twin, then I make a map on how actually the distribution of this flip up and flip down is about. And then we see that at least from this domain wall, it's very well defined. It's not something that is gradual. So it's obviously something due to the twin domain. And then roughly the angle that is made is also 60 degrees. It makes sense from the fact that you can only rotate by 60 times 1 times 2 times 3. So yeah, then everything makes sense now. That first I'm only looking at the thin termination. And then this termination, from here, I know now that there is a twin domain issue in this case. Well, then naturally I want to know, because I'm studying the magnetic Weyl semimetal, right? So whether any effect on the band structure when you go to the another magnetic domain, I mean magnetic configuration by raising the temperature, because now I'm really exactly at the lowest temperature that we have, which is 4 Kelvin. So we raise it up to 71. This is the temperature where we know the magnetic dome, the M should start to pointing along the C direction. Surprisingly, we don't really see any difference. So this is actually how it looks like when we just follow on one spot, raising starting from low temperature all the way to the 150K. 150K is everything is along the C direction. 70, you can say that there is some part that is still down, some part is already up. But then in any way, what we see is there is not really a big difference in here, which is, again, this is something interesting from the perspective of band structure, because from the calculation, actually, you should see a lot of changing. For example, from the calculation, whether the magnetic, if the M is pointing up, you should start to see something splitting in here, which is not what we see. This is how the EDC looks like. So we don't really see any difference unless everything is like buried under the ARPES resolution. But basically now our conclusion is that, well, surprisingly, there is no effect in the magnetism in here, at least on the one that is that we are focusing, which is along the gamma. Then what we want to say now, actually, this will be something really useful to be fit in further to the DFT calculation, because now we have another information, which is that on the gamma, you should see an electron pockets on the gamma, which is not what you expect, which is not what you expect from the tight binding. So because the tight binding will not give you anything on the gamma in here. So this is then my collaborator tried to play around with the U value to see actually which U value fit our recent ARPES, recent laser result, that roughly around 1.1 until 1.5, give and take, it's kind of like the best U value that we can use for the DFT. And then at the moment, he's still trying to figure out actually how the Weyl points looks like with this U value instead of the previous one that I displayed before, because that's using another U value that we still want to try to kind of like make the Dirac point looks like Dirac point around. Okay, now we don't care about the Dirac point, because now we have more like true band, which is coming from the gamma, close to the gamma, which is the electron pockets. And then that's now our gauge now to calculate. And then yeah, so then he kind of like concluded actually this might be the U equals to 1.3 is the best. The reason is because this actually match the center pockets that we are looking. And what about the outer pocket, you might ask? So actually the outer pocket is the effect of what we call the KZ broadening. So this might not, this electron pocket can only appear if you go to the other KZ, because the calculation that he did now is exactly at the KZ equals to 0. And for the KZ equals to 0, I'm expecting that it should be a pure electron pockets. And another evidence also why I can say that this is really coming from the KZ equals to 0, and this is not from the KZ equals to 0, because of the fact that the width of the peak is drastically different. They are like twice from each other. So it is already an indication that actually the broader peak that we have on the outer one is really coming from the broadening effect that we have by combining all the KZ together. Or in any way, so the main result that we have at the moment is that now we have a clear direction on where to go in the DFT. We really need to pin down all the calculation according to these electron pockets that we see, instead of whatever combinations of band that we are looking from the synchrotron. Well, unless there's another group maybe doing a nano-ARPES, which I do not know if there is any. I mean, there are only few nano-ARPES stations in the world, and then I know all of them, so I don't think that they're doing it. And so we're kind of like the one that is doing this spatial resolve on this iron tin. And yeah, so that's actually like the situation at the moment. And well, and actually now I want to this is kind of like the end of this Dirac versus Weyl thing. So if anyone has a question, feel free to give me any question, because this is like the end of this Dirac versus Weyl. For the next one, I will discuss a little bit on the recent progress that also we have about this project. Because interestingly, this is what we have been waiting for, kind of, that on the other sample that we cleave, we found more interesting band instead of just a boring either flip up or flip down, because now in here we have more. Although you can say that actually, well, I mean, in general, I found that there are 4 kinds of domain on this area that I'm looking now. And you can say that, well, actually, is it number 2 that you have found before? Yes, because number 2 is exactly that we saw before. And number 1 is actually we now attribute it to the twin domain of number 2. It's just happened that the wing is not seen because of the cross-section issue. So the interesting part is actually number 3 and number 4. This is something that we're still trying to figure out what is it. Most likely it's a termination, which is then this is number 4 will be will be the Kagome termination. The unanswered one is number 3. The reason why is this. Well, before that, yeah. So this is number 2. Number 2 is the same thing that we see before. This is the 3-fold that we see before. This is the number 4, the one on the bottom here. So interestingly, it's a different things in terms of the Fermi surface. Now it's more circular. And since this is very drastic from the 3-fold that we see, so most likely this is coming from termination. Although to really confirm this point, we're waiting for our collaborators to really calculate the surface states. And the interesting one that is unanswered to me is this guy, the one on here. So in principle, the important bit is that we found something interesting in the middle here, that if you plot, it's a 2-fold, which is interesting. Why? Like, why on earth a 2-fold band come out of the 6-fold system? I mean, if it's a 6-fold divided by 2 becomes 3, fine. Now it's 2-fold. So it's kind of like prompt me to really think that this might be the real signature of the Fermi arc, because Fermi arc now you have you're connecting 2 different pairs of well, but I do not have any solid evidence for that. But then at least this is just something that I share in here, that currently we're still like trying to figure out why this like 2-fold instead of 3-fold or 6-fold. And yeah, and then the next thing that I can share in here is also the work on this machine learning that we did. You know, because laser ARPES on each measurement is 2 gigabytes, 4-dimensional data, 10,000 data points, and this is only one measurement. And then after that, you need to move to another one, and then you move to another one. So that's why we think that, well, can we automate the fact that we need to do some kind of clustering in here, which is obvious. Like, I mean, you have a lot of tools out there to do clustering. So we try clustering. I mean, I try to do clustering on my raw data of this iron tin to see if actually any kind of resembles of this cluster that we may get, maybe then it may help me to really label instead of like laboriously go to one point, each point by point, and then try to label it. Unfortunately, if you just do a simple things, no, because you see here the result of it, the result from the PCA, from t-SNE, from t-SNE plus PCA. I mean, if you're familiar with the terms of this unsupervised learning, is that the answer is no. You will not see any natural clustering happening on this ARPES data. So this is kind of like making sad again at that time. And then so what do we do then? Yeah, okay, then since we are already kind of like in the middle of the way doing this laborious thing to really label everything, why don't we just do a CNN, the convolutional neural network? This is a supervised model, right? We see if then we can see whether this makes sense, whether this neural network can see and then can help us to classify and then draw us the domain, how the domain looks like from the data that we have. And this is the model that we use. Surprisingly, yes. So with about like 85% accuracy, with the model that I use, the CNN can give us how the domain of this number 1, number 2, number 3, and number 4 looks like in our real space, which is interesting. Then at least from here, we can study further how this domain actually distributed. And then looking at the way number 1 and number 2 are distributed, I kind of more convinced the way that this is number 1 and number 2 is basically just a twin domain from each other. And the interesting part is actually this number 4. So number 4 is is the minority. It's kind of like agree with the interpretation that this is actually coming from the Kagome termination. So this is just a different termination. So that means I want to say that number 1, number 2 is the stand-in termination, and number 4 is the Kagome termination, because this is just the minority. And then interestingly, that what about this number 3? So anything that has this 2-fold, where are they? They are located in the in between number 2 and number 4. So this may also give us a clue that this may not be really the Fermi arc that I thought before. This may be something just issue of, you know, you have a different termination. You may have some kind of step. You do not know what's happening. So this kind of like, at least what I want to say in here, well, good, the CNN can help. So, but then it's not really that helpful, right? I mean, if you're familiar with the concept of this supervised learning, that means this requires me to do all the labeling on each of the measurement. So then, like, this is only useful for iron tin. What if I'm measuring another sample, right? So if I make another sample, then do I need to spend another time to really label it? Well, of course, if you're using CNN, then you need to spend that time. So then that's the next idea that we had, which is actually then, why don't we just try to automate that? And then, well, isn't it that we already have the answer? That the answer is no. Well, actually, if you try to label the result of the CNN, try to label it on top of the result of the t-SNE or the PCA, actually, they are not really that jumbled together. They kind of like clustered, but they are close to each other. So this is where my collaborator comes in and then try to suggest, why don't we just use the representation learning? So then instead of doing it raw, putting it to the PCA, putting it to the t-SNE, why don't we try to process the data first, convert it into the representation, and then use this representation, try to plot it in the PCA and try to see if there is any clustering. The reason is because your CNN works. If your CNN works, that means at some point in between this middle layer, this is your representation. So that means actually if you use CNN and then this CNN can read your ARPES data, there is a certain representation that is automatically generated by this CNN algorithm. Why don't you just go directly to this representation and then use this representation to all of your data? It doesn't have to be this iron tin. It can be any kinds of ARPES data. So that's actually what we are doing at the moment, actually. And then the result is, yeah, the result speaks for itself, that you can classify my iron tin data into 4 clusters. Although yes, it's still close to each other, but at least it's better now. Without this guide of color, you start to see that actually there's a one cluster in here, another big cluster in here, and then another cluster in here. And then if you do this labeling, I label it from the CNN label, so just for guide for the eye. So it's very promising that actually this spatial resolve ARPES can, in the end, at least the first layer, I mean the first task, which is clustering, can be automated, not really that time consuming anymore. And then and again, this is only one kind of technique of representation, which is I'm doing what they call a SWAF technique from this Facebook research. You have another kinds of representation learning that we are that also we are at the moment trying, like Molko, Sinclair, and another guy like Biol. So all this has pros and cons, and at least from SWAF perspective in here, it can be used to classify this iron tin data. So yeah, then that's the final part of my talk, basically. So in summary, I have emphasized in here that actually the debate of this Dirac and Weyl points, we conclude that iron tin doesn't have a Dirac points because the ARPES data say so. No matter what the tight binding says, if the ARPES say you don't see any, you don't have any Dirac point, that means what you need to do is you need to modify your tight binding, which is they did. So last week, the same group that report the Dirac point upload another archive paper, and then now they include the interaction to the other layer, and then poof, you don't see any Dirac point. And then they're trying to say now you see a helical nodal line, which is, yeah, that defeats their first paper, basically. I don't know why they do that anyway. And then the next point is that I have demonstrated that actually laser ARPES is really useful. And then we found that with laser ARPES that yes, you have a lot of more complication happening inside this iron tin. You cannot just use the synchrotron as itself and then try to analyze it. You have more things to do. And then now everything is on the hand of the DFT group again to really calculate what is going on, and then tell me, like, back after they finish the calculation, where is the Weyl points, and then probably then I can relook my ARPES data to really see if we have any evidence of the Weyl points over there or not. And lastly, just a quick one that I have displayed, that actually in the future, the in the spatial resolved ARPES can have an automation going in the first layer or during the experiment, which is the clustering, by using this representation learning. So with that, I close my talk, and this is all. Thank you slide to all the collaborators that helped me, from PSI, from Genève, the sample grower, from Yimin's group, theory from PFL, and especially the recent collaborators from Hong Kong suggesting about this representation learning, which is a very fruitful discussion and also fruitful result. The draft is ready, waiting to be submitted. That's all.
Thank you very much, Sandy, for the wonderful talk. Okay, so this is a time for a few questions. If you have any question, Justin, do they just yell out or they have to?
No, yeah. So they can just simply unmute themselves. But sometimes they like to put their hands up and.
I see.
But
okay.
Just let them do whichever way they prefer.
Any questions from the audience?
Yeah.
No? Okay, so let me ask a question. So the first part of your talk is the disagreement between your data and the data from Linda. Yeah, I don't know whether that she was in MIT or Stanford,
MIT.
But anyway, in MIT. So the reason they got that, so it's not a matter of the fact that their sample is bad or whatever. It is what. So I'm trying to know why they see what they see, and which is what you don't see. Is it because theirs is not a micro-ARPES, and so they see kind of a average, or is it because you have photon energy dependence but they don't have, or what? Or their termination is different from yours, or what? What is the key difference?
Well, yeah, at the moment, it's well, as you see, also I'm also in contact with this group, like discussing the same thing. We kind of well, our data kind of agree, at least between my data and their data, that actually along the K point you don't really see something nice as can be seen in their figure C in here. So although I don't think that they will kind of admit it, but I think it's quite well known that in ARPES you can do symmetrization. Everything is so symmetry in here. So it might be either basically their cleaving is so convoluted with a lot of things. I don't know, maybe their twinning is happening more often than our sample, then they see a lot of things going on, and then they combine everything, so they might see this thing, rather than for us maybe we have a certain domain that is bigger, so we are not really that convoluted with the other twin domain. Well, at least so far I'm only talking about the physical domain rather than the magnetic, because at least from our laser ARPES we don't really see any influence on the magnet. So that's why now we're just talking about the way the physical things is. And I don't think this is really a determination, because again, from our result also, it shows that mostly it's thin termination. So I mean, if I'm being kind to them, I will just say maybe there are just too many twin domain happening on their system, so that's why they see the resemblance of this Dirac point. If I'm not being kind to them, then I will say you symmetrize your data too much, which is a valid point if you are coming from an ARPES group. Yeah.
So symmetrization is a common technique used in data analysis in ARPES, is it?
The symmetrization is a common thing you did for presentation. Like, I mean, if you want to make your data looks better, because at some point maybe your data is more lightened on one side, the other part is not really that lightened, because maybe your sample is not really good on that part. So you just want to make it good, but at least you should know that you are symmetrizing something that is really symmetrized in the first place. But if you're not sure, like in this case, then you might see something artifact, right? Like in this case.
Okay,
but again,
okay.
Yeah.
Okay, good. Thanks. And one of your last slides, when you talk about the representation stuff, can you maybe give a one minute explanation of the different the previous what is PCA and
PCA
T-SNE and all these?
So this is the unsupervised learning technique. So the idea is PCA is principal component axis. So then this is
I see. So this is a principal component analysis.
Yeah, and then you just try to project, and in this case I just assume it's 2D. I mean, you might also argue with me that you might project it to a certain higher dimension, but no, I mean, the purpose of this one, I just want to have something helping me during the measurement. So I just want to see something if I mean, like 2D, if it is really going on, and then it turns out, well, it's not really that bad, right? I mean, everything is so clustered, it's just everything is close to each other. So I just want to have something to really pull them apart. And then,
so the four colors means what? The four different domains are?
The four, is exactly this one. So the four colors is just what I label from the one that I get from the CNN. Yeah.
I see. So these are like your four principal components kind of thing. Is it?
Well, in this case, I only two principal components.
Okay,
then,
sorry. Okay.
And then and then my hope at that time is I just want to see if the PCA can separate it into four different clusters. So if it can separate, that means in the future when I redo this experiment, or I redo another experiment with another sample, then I can just do PCA, see the cluster, label it, and then I go back to my data and then see how the domain looks like.
Can you go back? Can you go to your representation theory? This one.
Yeah.
So what are your axes are your two principal components again?
This is exactly the same. Okay, in this case I use the PCA plus T-SNE. That means is this guy is the one on the right. So it's a PCA plus T-SNE.
Okay. Yeah. And so what additional information does this figure have compared to the PCA plus T-SNE?
Yeah, so it's the representation. So then what is being the input to the PCA plus T-SNE is not my ARPES data. Initially, the input is my ARPES data. Well, there is some pre-process, but anyway, it's the raw ARPES data that I put in the PCA plus T-SNE, which is basically the idea of that is then it's trying to see if there is any relation between this pixel to another pixel, blah blah blah. So then the answer is no, right? So you don't really see that. And then, but in the CNN, CNN can classify them. So that means somewhere in here is the representation that is being used. That's actually the idea. So representation means instead of I'm putting the raw ARPES data, I convert this ARPES data into its representation. And then what kind of representation is this? It depends on the algorithm that I use. And then in this case, I'm using this swapping assignment between multiple view, blah, blah, blah. This basically is doing some contrastive technique. Contrastive technique meanings that it tells the neuron, this is my real image. Let's say this is my cat image. And I do some transformation on this cat image. And I tell you, this is not my cat image. So please see what kind of contrast that I have and take this in your neuron. Remember this is different. And then it will kind of encode it in the layers itself. Then, okay, this is the representation. So like, for example, I can tell you that what kind of representation that is presented in here. I don't have it in here, but at least in the middle layer, it's the representation understand that, first of all, there is a Fermi level, which is interesting. I mean, like, I'm still trying to understand, but at least the representation can understand there is a Fermi level. So that means it understands where is your Fermi level, first of all. And then it can show me a very like contrast line around here. Okay, so that means I can understand that my neuron is understanding that there is a band in here. So that's why then it can understand this band. I mean, this picture and this picture are different because you have a band here, and then you only have and then you have a band here. You do not have a band in here. So that's why they can kind of like separate them together. That's how I understand it at the moment. And then this kind of representation can be different if you use a different technique. That's it.
So every dot here represents what? Every dot.
Every dot represents the data. like the X and Y. So the X point Y, your
Oh,
here,
every dot
yeah,
is a particular XY
here, yeah, let's say
coordinate.
here, yeah, let's say here, let's say here, let's say here, yeah. So because that's the whole idea, right? I mean, you have an X and Y, and then on each X and Y is your dispersion cut. I want it to be classified. I want it to be to show me what domain is this. I mean, how the domain looks like. So that's why you can do it by go one by one, label it. Okay, number one, number two, but then it will be like 10,000 data for each of the experiment, and then typically your sample dies within 24 hours. So then you can only do the experiment within 1 hour. So within 1 day. So you really need to make everything very fast, right? So yeah, this is kind of
so
like
your method is applicable to what other kinds of measurements?
The representation itself is actually applicable to any image. Like
Okay.
I don't know, maybe if you have some STM image and then you try to see, okay, you try to differentiate something in the picture, you can do it with representation.
I see. Okay.
But of course, I mean, if you really go to this representation, that means you are sure that the typical way doesn't work. Like I know the nano-ARPES group by Eli in Berkeley, they use the normal K clustering. I mean, if any one of you in here knows about this data science, I mean, you should be familiar with PCA, TSNE, K clustering, whatever. So they use this rudimentary technique, and then they claim that they can do some domain mapping on the graphene. That method has a drawback, which is, well, that means you really need to make the band structure exactly at that point. While if you are using this representation, it doesn't matter where your band structure, you can move your Fermi level up and down, because that's something that I didn't really expect before, because wow, it can really knows where is the Fermi level. So that means I can move my band structure up and down, and then it can knows this is the Fermi level, and then according to this Fermi level, where is my band. This is very useful, especially if you only have conduction. If you only have a valence band without any Fermi, without any clear conduction band. I mean, your valence band can move up and down, and then if you use the normal technique, a little bit hold up will be treated as a different band, although they may not be different, right? So then, yeah. So this is like the details that is still going on at the moment.
Thank you. Any other questions from the audience? Justin, you have anything?
No, I think I asked the main questions I had. I actually had a question about the Kagome flatbands and how you differentiate that from any surface states. So you made an interesting comment in the middle about the way to differentiate surface states was looking at their dispersive character.
Yeah. So,
but you were also looking at Kagome systems which have flat bands. So flat bands, as I understand, don't disperse as well.
Correct.
So how would you differentiate between, say, a putative surface state and a flat band in the bulk? Yeah, so that was more like a technical kind of question.
Yes, okay.
Yeah.
To differentiate that is straightforward if, let's say, your flat band lies not close to the Fermi level. So if it is really away from the Fermi level, like deep in 1 eV or 0 point something eV down, the FWHM will be quite big. So that's already an indication that this is really coming from something inside, because surface state should have a very sharp peak width when you, like, if you like, for example, when you do this kind of analysis, if it is surface state, it will be very sharp. That's one of the indication. But sharp can also mean you are close to the Fermi. You're close to the Fermi. So I think at some point there is a publication about the cousins of this Argentine, the Fe3Sn2, the 1-1, and they claim that they see the flat surface. The way they argued that is the flat band is really just using the tight banding, and then I believe they do something about, okay, they follow the orbital, and then they do the DFT. And although in DFT you will not see any kinds of flat things, but since this orbital in the DFT is exactly the orbital that is making this flat band. So they claim that, okay, this flat band evolves to this one. Therefore, this is the ARPES that we see. Therefore, this is the flat band, which is I don't like. So that's what's happening so far in the ARPES world about claiming this flat band. And yeah, so yeah, again, yes. So that means if you really want to differentiate between this surface or not, yes, true. Do a photon dependence. If they don't change, it might be surface. And also the indication is if it is surface, it's very sharp. You see it in comparison with the other band that is on that energy also. If it is really sharp, then it's obviously coming from the surface.
I see. Thanks. That's clear. Yeah.
Oh, and the other one is, yes, ARPES by itself can only say this is most probably surface state. In the end, it's really, I mean, we really need the help from DFT to really say, okay, if the DFT match with the ARPES, then this is really the marriage. Like from us, we can only say, yeah, for example, like this, right? I mean, we can only say, I don't see gap. Is it a Dirac point? I don't know. Something like that. You really need to calculate, okay, from the tight binding, it seems like a Dirac point. Okay, so then is this a Dirac point? Maybe within the context of their data, okay, they can claim that this is Dirac point. But then again, if you try to change the photo energy, then you start to see that it is not. This is changing, blah blah blah. And interestingly, actually, they did photo energy in here. I think do I have it? Yeah, here they did. So they did a different photo energy.
Yeah.
Okay.
Sure. No. This is yeah. That's going to more detail than
yeah
than I need. But okay. Sure. Yeah.
So yeah. Anyway.
Yeah. Okay. So I think it's been some time already. Thank you very much for your talk. Let me just stop the recording.